Today we'll discuss section 3.7. Before we jump into this section, let me go back to section 3.5. In section 3.5, we discussed in particular how to solve systems of linear equations. So, suppose we have a system of linear equations. Step 1, write down the augmented matrix. Step 2, apply elementary row operations to come up with this form. But now question is, what is this form? Can we describe formally, say, the ultimate goal of these elementary row operations? And this is why we care about section 3.7. In section 3.7, let me actually start with page 5. In section 3.7, we discuss a so-called echelon form. What is an echelon form? Please take a look at this picture. On this picture, we see three types of symbols: zeros, black squares, and asterisks. Zero means the number 0. By black square, we mean any non-zero number. And by asterisk, we mean just any number. Now, an echelon form satisfies a bunch of rules. Most important rule is the next black square, the black square from the next row, should be from the right of the previous black square. So once again, let us compare, say, row number 1 and row number 2. Know that this black square is on the right. Row number 2 and row number 3. Know that this black square is on the right. Row number 3 and row number 4. Same. Row number 4 and row number 5. This black square is on the right. Next, beneath and to the left from each black square, we have zeros. Note, let us go back to section 3.5. Note that here in this example, over here, this is not an echelon form yet, because these three ones play a role of black square, but this black square is on the right from this black square. But it should be all the way around. Now, what we see in front of us here is an echelon form. Black square, black square, black square. Next example. Over here, again, this is already an echelon form. Black square, black square, black square. This is also an echelon form. Black square, black square. Everywhere else, to the left and beneath, we have zeros. In Appendix 1, I have more examples. So once again, here is a numerical example of what we just discussed. Black square, black square, black square, black square, black square. By the way, we will call black squares pivots. So in this matrix, we have 5 pivots. Pivot number 1, pivot number 2, number 3, number 4, number 5. Now, over here, we have examples of echelon forms and non-echelon forms. So please take a look. Over here, this is an echelon form because each next black square is on the right. And to the left and beneath, we have zeros. This matrix is not in echelon form, because we have 2 black squares in one column. Now, sometimes we have a row that completely consists of zeros, but such a row should be on the very bottom, not somewhere in between. This is not an echelon form. Now, this matrix is again of an echelon form, but if we switch a row number 1 and row number 2, the resulting new matrix is not an echelon form. Here, echelon form, not echelon form. Echelon form, not echelon form. Lastly, sometimes we start with one or more zero columns. This is an echelon form. So we can have a zero column on the front, on the back, on the bottom, but we cannot have a zero row on the top. This is not an echelon form. Any questions so far?
Wait, I do, yeah. Wait, so for that
Yeah.
last example that you showed where the zero
Yes.
is on the top, can't
Yes.
you bring the second row to the first row and the third row to the second row?
Absolutely. We can apply elementary row operations to come up with an echelon form. Just switch row number 1 and row number 2, then switch row number 2 and row number 3. We will get an echelon form. But this particular matrix is not an echelon form. Does this make sense?
Okay.
So one of the goals when we apply elementary row operations is to come up with an echelon form. Now, please take a look at this very important theorem. Remember, in the same section at the end, we discussed 3 examples. In all 3 examples, when we apply elementary row operations, we get a zero row. But in example number 1, this system has only one solution. In example number 2, no solutions. In example number 3, infinitely many solutions. So despite the fact that in all 3 cases we have a zero row, we have 3 different outcomes. One solution, no solutions, infinitely many solutions. Question is, looking at an echelon form, is it possible to know for sure how many solutions does a system have? The answer is yes. Please take a look at this very important theorem. So consider the following system: AX is equal to B. If we apply elementary row operations to A and obtain a row of the form 0, 0, 0, and so on, non-zero. Oh, by the way, guys, I made a misprint. Here, instead of matrix A, should be augmented matrix A, and then last column should be B. I will update it. So, if we apply elementary row operations to the matrix AB, and if we have a row of the form 0, 0, 0, non-zero, then this system has no solutions. Then, if this is not the case, if we apply elementary row operations to matrix A, and we have same number of pivots as variables, then the system has exactly one solution. Lastly, if we apply elementary row operations to A, and the number of pivots is lesser than the number of variables, then we have infinitely many solutions. It's exactly what we have here. So let us consider the following augmented matrix. This. We apply elementary row operations, and we see that there are 2 pivots, which is equal to the number of variables. And there is no row which completely consists of zeros, except for the very last element. Conclusion, our system has exactly one solution. Case number 2, we apply elementary row operations, and we get a row which completely consists of zeros, except for the very last term. Conclusion, system has no solutions. Lastly, we apply elementary row operations, and we see that we have 1 pivot and 2 variables, and there is no contradiction. System has infinitely many solutions. Folks, any questions here?
So to know, an automatic tell for to know that there's no solutions is if in your augmented matrix you have all zeros and then a constant. Is that correct?
Not in augmented matrix. So we start with an augmented matrix.
Right.
Then we apply elementary row operations in order to come up with an echelon form. If an echelon form has a row which completely consists of zeros, except for the very last element, like here, then the system has no solutions. Does this make sense?
Yep.
Other questions?
So whenever we have a system of equations, we represent it as an augmented matrix, right?
Yes, yes. So in other words, this is a misprint. I will correct it. So if an echelon form of a matrix A, B, and by the way, same here, we can put here AB and here AB.
Okay. So the number of pivots that you have that you have in your augmented matrix, this is supposed to represent how many solutions you would possibly have.
It does not really represent the number of solutions. The rule is a little bit different. If the number of pivots is equal to the number of variables, we have exactly one solution. If the number of pivots is lesser than the number of variables, we have infinitely many solutions.
Yeah. So I was just trying to ask, like, for the augmented matrix, because I guess that was what I was initially confused about. And I was trying to like figure out the property sometime yesterday and I couldn't remember. And it was because I was trying to I was working with regular matrices when I needed an augmented matrix.
Yeah, we need augmented matrix. Yes. Step one, start with the augmented matrix. Apply elementary row operations until you get an echelon form. And then apply this theorem. So here, once again, instead of A, we should consider the augmented matrix. I'll update it.
Yeah, that makes sense now.
Other questions?
Wait, can you repeat the definition of a matrix versus an augmented matrix?
Oh, very good. So this system can be written as AX is equal to B.
Yep.
A is the matrix of this system. AB is the augmented matrix.
Okay.
So AB is this. A is just column number 1 and column number 2.
Okay.
Other questions?
I kind of have like a formality for this
Yeah.
type of thing. So we have AX equals B and that has infinitely many solutions.
Yes.
Or it has, so we don't say that like X has infinitely many solutions. We say the system.
No, not X. X represents a solution. AX is equal to B is a system.
Okay, so when we have this system, we say this system has like all these solutions.
Yes.
Okay.
Or we can say this matrix equation has a solution or does not have a solution.
Okay, that makes sense.
Other questions?
I have a question.
Yes.
Statement. It doesn't make sense for you to have more pivots than variables, right?
Yes, we cannot have more pivots than variables because, please take a look at this. Here we consider A and B when we say otherwise. Otherwise means if we don't have such a row, then all pivots will be everywhere except for the last column. Therefore, the number of pivots cannot exceed the number of variables. Does this make sense?
Yes.
So once again, the only case where we have a pivot in the very last column is this. But if this is the case, system has no solutions. Now suppose this is not the case. This means that pivots are somewhere here, which means we have either same number of pivots as variables or lesser. Did I answer the question?
Yes.
Other questions?
I know the definition is right here, but could you go over it, what the pivot position is?
Yes. Pivots are these black squares. Pivot column is a column with a black square. Does this make sense?
Yes, thank you.
Mhm. Other questions?
Can pivots be 0, or do they have to be a
No, no, no. Black squares represent any non-zero number. So 0 means 0, asterisk any number, black square any non-zero number. Black square cannot be 0.
Got it. Thank you.
Other questions?
If there's a black square in the last column, does it still
Yes.
pivot?
Yes, it is a pivot, but once again, if we consider the augmented matrix, so once again, I will update it. Instead of A will be this. So if we have a pivot in the last column, system has no solutions. Does this make sense?
Yes, it does. Thank you.
For example, please take a look at this. Appendix 1. We have pivots in every column. Now, before we jump into systems, let me show you one really powerful application of pivots. So please take a look. Let us go back to section 3.3. In section 3.3, we realized that it takes quite some time to determine whether or not vectors are dependent or independent. In order to prove that these vectors are dependent, we set up a corresponding system, we solve the system, and then we see, okay, system has infinitely many solutions. Now, pivots allow us to come up with the same result much easier. Please take a look at this very important theorem, which is on page 13. We start with several vectors from Rn. Step 1, create the following matrix, V1 and so on Vm. V1 and so on Vm are columns of this matrix. Then we apply elementary row operations to come up with an echelon form. If this echelon form has a pivot in every column, then vectors are independent. In other words, if we have the same number of pivots as vectors, vectors are independent. Case 2, if the number of pivots is lesser than the number of vectors, vectors are dependent. Moreover, if we consider span of these vectors, then pivot vectors form a basis of this vector space. The dimension of this vector space is equal to the number of pivots. Lastly, if we consider an echelon form has a pivot in every row, these vectors span Rn. Moreover, this is if and only if statement. Example, let us go back to our vectors u1, u2, u3, v1, v2, v3. We create the corresponding matrix. We apply elementary row operations to come up with an echelon form, and we see that the echelon form has only 2 pivots, but we have 3 vectors. Conclusion, vectors are dependent. Moreover, vectors u1 and u2 is a basis of span of these 3 vectors, and the dimension of this vector space is 2. Furthermore, these 3 vectors do not span R3 because we do not have pivot in every row. To the contrast, v1, v2, v3 are independent because the number of pivots is equal to the number of vectors. Moreover, vectors v1, v2, v3 form a basis of span of v1, v2, v3. And the dimension of this vector space is 3 lastly, these three vectors span R3 because we have a pivot in every row. Questions?
Yeah, I have a question. So the reason that you know that U1 and U2 are form a basis is because the pivot is in that row?
Yes, exactly. So
Okay.
do not confuse 1, 0, 0 and -2, 1, 0 is not a basis. In order to find a basis, we have to go to the original matrix and mark pivot columns.
Okay.
U1, U2 is a basis. Was that your question?
Yeah, that was my question. Thank you.
Wait, can you repeat the definition of a basis again?
Yes. So let us actually go back to, yes, dimension of vector space. Here is definition of basis. Yes, it's over here. A basis is a set of linearly independent vectors that span the whole vector space. So U1, U2 form a basis of span of these three vectors. Means these two vectors U1, U2 are linearly independent, and these two vectors U1, U2 span the whole vector space. Does this answer your question?
Yes, it does. Thank you.
So in simple words, a basis is the smallest number of vectors that can generate the whole vector space through their linear combinations. Other questions?
Vectors U1 and U2, they span R2, right?
No, they do not span R2 because these two vectors are from R3. They cannot span R2. They do not belong to R2.
How are U1 and U2 a basis if you would need three vectors to make a basis for R3?
No. So U1, U2 is not a basis of R3. It's not a basis of R2. U1, U2 is a basis of span of U1, U2, U3.
Oh.
Yes, step one, consider the following vector space. Span of U1, U2, U3. A basis of this vector space is U1, U2. To the contrast, span of U1, V2, V3 is equal to R3. Span of U1, U2, U3 is not equal to R3. Does this make sense?
Yeah.
Other questions?
Just to reiterate, what is the span of U?
Yes, span. What is span? Please take a look at this definition. Span is the set of all linear combinations of given vectors.
No, I meant what is the span of the U vectors, the U vectors?
Oh, here, span of U1, U2, well, we cannot really, it's not R2, it's not R3, it's just the set of all linear combinations of U1, U2, that's it.
Okay, got it, thank you.
If you ask me about a geometric interpretation, yes, so U1 is a vector in three-dimensional vector space, U2 is a vector in three-dimensional vector space. Now let us consider a plane that goes through these two vectors. This will be span, geometric interpretation of span. Does this answer your question?
Yeah.
Other questions?
I have a question.
Yeah.
So after we reduced that matrix into row echelon form,
yes,
we receive a lot of information about the pivots and stuff. Can you repeat that information again?
So most important information is the number of pivots and location of pivots. So why we need the number of pivots? Because we want to compare the number of pivots and the number of vectors. If the number of pivots is lesser than the number of vectors, vectors are dependent. If the number of pivots is equal to the number of vectors, vectors are independent. Then location, pivot columns of the original matrix form a basis. Lastly, if we have a pivot in every row, these vectors span Rn. Was that your question?
Yes.
Other questions?
Can you scroll down to the part of V1, V2, V3?
Yes.
And then can you reiterate what the difference was? Because they're the same matrix, right? But you said that the difference is
No,
one
these
spans
are
R3?
these are different matrices. Here we have 6, here we have 7.
Okay, okay. Sorry.
And echelon forms are different. Here we have 2 pivots, here we have 3. Other questions?
So to be sure, if it's linearly independent, if there's a pivot in each column or each row?
Each column. If we have a pivot in each row, these vectors span Rn.
Okay, and is it required for A to be a square matrix?
No, absolutely not. So here, know that here M, here N.
Okay.
It doesn't have to be square. Other questions?
I have a question.
Yes.
So what if your vectors are made up of polynomials? Would you still be able to use this?
Okay. If we have polynomials, let us go back to this handout. So here we have polynomials. In order to determine whether or not these polynomials are dependent or independent, let us consider their linear combination, expand parentheses, regroup, and then set up a system. However, in Appendix 5, I discussed a little bit different approach. So step 1, attach to each polynomial a corresponding matrix column formed from the coefficients, and then apply the previous theory. So these matrix columns together, come up with an echelon form, and count the number of pivots. Done.
All right, thank you.
Sure. Other questions?
So you said it didn't have to be a square matrix.
Yes.
But if it was a rectangular matrix, then wouldn't it be impossible to have a pivot in every column?
Very good point. If the number of columns is bigger than the number of rows, these vectors are automatically dependent. Absolutely. Other questions?
I wanted to ask a similar question. So I wanted to ask, like, in a matrix where you have columns greater than rows, right? Actually, wait. I actually mean more rows than columns. Never mind.
Okay, more rows than columns. So it's vertically stretched.
Yes, vertically stretched.
Yes.
So you have a vertically stretched matrix.
Yes.
However, I had a hard time proving that this was linearly independent when I had a row of zeros.
Well, think about this example. Add 0, 0, 0 here.
Yeah.
Then here we'll have 0, 0, 0. But vectors are independent because we have a pivot in every column. Done?
Okay. Okay, that's what I was wondering. Thank you.
Other questions?
Wait, I'm a little confused. Wouldn't row number 4 not have any pivots though?
Yes, in row number 4, we don't have pivots, but we need a pivot in every column.
Oh, okay. Never mind. I got it.
Yeah. Other questions?
So for independence, independence is different than spanning Rn. If you had
yes.
Yeah. So like in this echelon form on screen, that spans Rn, where n is your number of columns or whatever.
Yes.
Right.
So these 3 vectors span R3 because we have a pivot in every row.
Right. But that isn't. You can have a rectangular matrix which can be independent, but it wouldn't span Rn or whatever.
Absolutely, absolutely. Just consider vectors v1, v2 only. They will be independent, but they will not span R3. Okay, now let us go back to our systems of linear equations. Please take a look at section 3.5 again. So, in this example, in example number 1, we created the augmented matrix, and then we applied elementary row operations until we got an echelon form. Then we switched to the corresponding system and solved this system. We did same thing here in this example. Again, we apply elementary row operations until we get echelon form and then switch to the corresponding system. However, in this case, we obtain an echelon form, but then all of a sudden we keep applying elementary row operations. Why? Here is the answer. Please take a look at the so-called reduced echelon form. The difference between echelon form and reduced echelon form is the following. Now, instead of black squares, pivots, we have ones. So in reduced echelon form, a pivot is not a non-zero number. In reduced echelon form, a pivot is necessarily 1. Difference number 2, in echelon form, beneath and to the left from each pivot, we have zeros. In a reduced echelon form, not only beneath and to the left, but above each pivot, and let me stress this word, each pivot one, we have zeros. I've never said that above each one we have 0. For example, if we have 1 here, we don't really need zeros above this one. Above each pivot 1, we have also zeros. Going back to this example, what we see in front of us here is an echelon form. Pivot number 1, pivot number 2, zeros to the left and beneath. But this is not a reduced echelon form because we have non-zero element above this pivot 1. This is not a pivot 1, but this is a pivot 1. Now this is the reduced echelon form because not only to the left and beneath, but above this pivot 1 we have 0. Now you may ask me a question, why in previous examples we did not need reduced echelon form, but in this example we need reduced echelon form? The answer is, guys, remember we have 3 cases. A system has no solutions, 1 solution, and infinitely many solutions. So if an echelon form tells us that our system has either no solutions or 1 solution, we don't really need reduced echelon form. However, if we see that our system has infinitely many solutions, keep applying elementary row operations in order to come up with a reduced echelon form. Only after that, switch to the corresponding system. Moreover, note that once we come up with this system, then we move the z terms to the right. And question was, why we move z terms to the right, not x, not y? Here is the rule. We move to the right only 3 variables, and we leave on the left only basic variables. Well, question is, what is a free variable? What is a basic variable? Answer is, variables that correspond to pivot columns are so-called basic variables. Variables that correspond to non-pivot columns, and here is a non-pivot column, correspond to free variables. We move to the right only variables that correspond to non-pivot columns. We leave on the left only variables that correspond only to pivot columns. It's exactly what we do here. Please take a look at this. Here's a system. It's augmented matrix, echelon form. Echelon form tells us that our system has infinitely many solutions because there is no row that completely consists of zeros except for the last element, and the number of pivots, which is 2, is lesser than the number of variables, which is 3. So our system has infinitely many solutions. Therefore, we keep applying elementary row operations until we get the reduced echelon form. After that, we switch to the corresponding system and move the free variable, and know that in our case, column number 1 and column number 3 are pivot columns. Therefore, column number 2 is the only non-pivot column. Therefore, x2 is the only free variable. We move the free variable to the right, and here is a complete description of all solutions. Let me discuss 2 more examples. Skip this for a moment. We will touch it later. Here's an example. Here's matrix A, here's matrix B. We have system AX is equal to B. As before, augmented matrix, echelon form, it tells us that the system has infinitely many solutions because the number of pivots is 2, which is lesser than the number of variables. We apply elementary row operations until we get a reduced echelon form, and then switch to the corresponding system. We move the free variable to the right, and we are done. Why x3 is the free variable? Because pivots are in column 1 and column 2. Last example. Here's a homogeneous system. We apply elementary row operations until we get echelon form. We see that there are 2 pivots and 5 variables. Therefore, system has infinitely many solutions. We get a reduced echelon form, switch to the corresponding system, and move all 3 variables to the right. Any questions?
Could you just briefly go over again how to determine if it's a free variable?
Yes. So free variables are variables that correspond to non-pivot columns. Please take a look at this. Here's pivot number 1. Here is pivot number 2. So column number 1 and column number 3 are pivot columns. Column number 2 is not a pivot column. Therefore, x2 is a free variable. x1, x3 are basic variables. Basic variables correspond to pivot columns. Free variables correspond to non-pivot columns. Did I answer the question?
Yeah, thank you.
Other questions?
Can you go over how to turn echelon form into reduced echelon form? I'm kind of confused.
Well, we just apply elementary row operations.
Okay.
Yeah. So once again, tilde means we apply elementary row operations to jump from here to here. We keep applying elementary row operations until we get reduced echelon form. And reduced echelon form, pivots are 1s, and then to the left, beneath and above each pivot 1, we have zeros. Did I answer the question?
Yeah, I got it. Thank you.
Other questions?
Can you explain why we need reduced echelon form and like?
Yes. Okay. Very good question. Why we need reduced echelon form? Well, please take a look at this example. Imagine that we jump to the corresponding system, not from reduced echelon form, but from echelon form. Well, if we do so, we'll get the following system: x plus y minus 10z is equal to -4, and then y minus 3z is equal to 1. Then, once we move a -10z and -3z to the right, we will not come up immediately with the ultimate goal, because equation number 2 will be fine. Y is equal to 1 plus 3z. But equation number 1 will not be fine. On the left, we'll have x plus y is equal to -4 plus 10z, which means we have to tweak this system a little bit more in order to describe all solutions. However, if we come up with reduced echelon form and move all 3 variables to the right, solution follows immediately. Does this make sense?
Yes, thank you.
Other questions?
So in this case, there's a pivot point in the second column of the reduced echelon form.
Yes.
Whereas, like, I guess, like an example before it, it would have a pivot point in the third column instead.
Oh, well, it depends. Location of pivots depends on the underlying matrix. Sometimes we have pivot in column number 1 and in column number 2. Sometimes we have pivots in column number 1 and column number 3, and so on. In this example, we have pivots in column number 1 and column number 3. It depends on the underlying matrix.
Thank you.
Other questions?